Time and space are like a fabric, like rubber, like a trampoline net. However, if you stretch the trampoline net too much, it can rip perhaps, and perhaps you can turn this trampoline net into a pretzel and allow yourself to go backwards in time. As physics continues to progress, we find ourselves pushing the boundaries of our understanding. Surprisingly, it appears that two of the most fundamental and intuitive concepts, space and time, might need to be reconsidered to enable further advancements. Recent images captured by NASA's James Webb Space Telescope have unveiled an astonishing anomaly in deep space, reshaping our understanding of cosmic history and challenging our previously held beliefs. So what exactly did this powerful telescope reveal about the nature of time itself? Does the James Webb Telescope provide evidence that time may not be as we perceive it? Join us on this journey as we delve into the groundbreaking findings of the James Webb Telescope, which have left the space industry astounded, and consider the intriguing possibility that our conventional understanding of time may need to be redefined. Many of the fundamental questions that have occupied astronomers over the last 50 years are being addressed by the James Webb Space Telescope. It is one of the most expensive engineering projects ever attempted, costing $1 billion. Our understanding of distant planets and deep time is already being revolutionized by the James Webb Space Telescope. The feeble light emanating from the farthest galaxies in the sky, light that left its source long ago and so portrays the galaxies as they appeared in the distant past when the universe was young, can only be collected and focused by a mirror so large and smooth. When unexplainable forces conspired in the shadows and the first star-forming farms emerged, we would observe the darkest, furthest galaxies still in the midst of formation. An exceptional mirror, however, is not nearly enough to read that early chapter in the history of the universe. To learn the nature of those first, probably enormous, stars, to learn about the invisible matter whose gravity coalesced them into existence, to learn about the roles of magnetism and turbulence, and to learn how enormous black holes grew and worked their way into the centers of galaxies. Nothing like the James Webb Space Telescope has ever been sent into orbit. It has investigated the very earliest stars in the universe, finding proof of extraterrestrial life and even physically defying convention. Stars, galaxies, and supermassive black holes were discovered by the Hubble Space Telescope to have existed much earlier in cosmic history than previously thought, and to have experienced significant alterations since then. We now know that the cosmos is shaped by dark matter and dark energy. With the help of the Kepler telescope and other instruments, we have observed that galaxies are decorated with a wide variety of planets, including billions of potentially habitable planets in only our Milky Way. These discoveries have sparked a number of queries that the James Webb Space Telescope is already attempting to answer. Astronomers are referring to 6 huge, old galaxies discovered by the James Webb Satellite Telescope as universe breakers because their existence could contradict accepted cosmological theories. The objects are much larger than was previously believed feasible for galaxies so soon after the Big Bang, dating to a time when the universe was only 3% as old as it is now. The discoveries, if confirmed, would cast doubt on scientists' theories of how the first galaxies arose. Joel Leha, an assistant professor of astronomy and astrophysics at Penn State University and a research co-author, remarked, "These objects are way more massive than anyone expected. Currently, we anticipated discovering only young, fledgling galaxies, but what we stumbled upon were galaxies as mature as our own, a revelation that defied our previous understanding of the early universe." These revelations were made possible through the utilization of data from the initial dataset provided by the Webb Space Telescope, equipped with infrared sensors capable of capturing light emitted by the most remote stars and galaxies. Dr. Erica Nelson, a co-author affiliated with the University of Colorado Boulder, made a fascinating observation while scrutinizing the images, a cluster of hazy dots that exhibited exceptional brightness and an unusual reddish hue. In the realm of astronomy, redness serves as a proxy for age due to the stretching of light, or redshifting, as it traverses the expanding universe. These enigmatic galaxies appear to be approximately 13.5 billion years old, placing them between 500 million and 700 million years following the Big Bang. Although the James Webb Telescope has previously detected galaxies that are roughly 350 million years old, these newly discovered galaxies were notably larger, with a mass equivalent to tens to hundreds of billions of sun-sized stars, comparable to the Milky Way. This revelation challenges existing cosmological principles and our understanding of the formation of the first galaxies. Tiny dust and star clusters, according to current theories, suggest that the universe experienced a brief period of rapid expansion, followed by several 100 million years of cooling, which permitted gas to condense and give rise to the first stars and galaxies. This era is known as the Dark Ages. However, the discovery of such massive galaxies so soon after the Big Bang suggests that the Dark Ages may have been a more vibrant period than previously assumed, marked by extensive star formation. Dr. Emma Chapman, an astronomer at the University of Nottingham, emphasizes the need for further observations to substantiate these findings before established models can be re-evaluated. She underscores the importance of spectrum photos, which can provide more precise distance data and enable more accurate mass estimations. Throughout the history of physics and astronomy, surprising discoveries like this one have frequently led to paradigm shifts in our understanding of the universe. It's a reminder that science depends on breakthroughs, and as new revelations surface, existing theories are subject to revision and improvement. For over a millennium, humans held the belief that Earth occupied the central position in the solar system. However, Nicholas Copernicus boldly challenged this notion, proposing that we were just one of many planets orbiting the Sun, offering a simpler explanation for the celestial system. Despite staunch opposition, the geocentric theory gradually crumbled under the weight of evidence, notably from newly developed telescopes. The motion of planets around the Sun found its explanation in gravity, as later elucidated by Isaac Newton. He introduced the concept that all objects with mass exert gravitational attraction on each other. In this framework, the Moon orbits Earth because of Earth's gravitational pull, just as Earth orbits the Sun due to the Sun's gravitational influence. Newton's theory reigned supreme for 2.5 centuries until Albert Einstein's arrival in 1915 with his groundbreaking general theory of relativity. Einstein's theory revolutionized our understanding of gravity. He envisioned gravity not as a force but as a consequence of curved spacetime, presenting the universe as a seamless four-dimensional fabric known as spacetime. According to this concept, Earth's orbit is a result of our planet, following the curvature created by massive objects like the Sun, which warp the spacetime around them. This warping gives the appearance of gravitational attraction, as described by Newton. Einstein's spacetime model held sway for over a century, but its supremacy faces a significant challenge due to its incompatibility with quantum theory, another prominent framework in the world of physics. The quantum realm is known for its strange and counterintuitive phenomena, such as particles existing in two places at once until observed. The interplay between these two foundational theories, general relativity and quantum theory, remains an ongoing and intriguing puzzle in the world of physics. The quest to reconcile these two giants continues to drive scientific exploration and discovery in the ever-evolving field of theoretical physics. We can only ascribe probabilities to the likely outcomes prior to an observation. Time, as we know it since we learned to tell time on a clock, seems to disappear when you study physics until you get to relativity. According to others, there is no absolute time or space, which is the fundamental tenet of relativity. Nothing is absolute. When trying to explain time in the context of the cosmos, it helps to start with the straightforward notion that time evolution simply concerns the interactions between specific portions of the universe and the item you call your clock. However, not all physicists are prepared to relegate time to a subordinate position. Anglican clergyman and quantum physicist John Polkinghorne is convinced that time moves in a genuine and unrelenting direction. Relativity is a mistaken argument, he added, because no observer has knowledge of a distant event or the simultaneity of different events until they are unmistakably in that observer's past. In light of the fact that it is impossible to prove that the future actually exists, this argument concentrates on how observers arrange their descriptions of the past. The idea of a static block cosmos made up of both space and time is rejected by Polkinghorne, with time being measurable and malleable in relativity but supposed to be background and not observable in quantum mechanics. There is a major disagreement between these two theories. While humans perceive time as being fundamentally real, according to many scientists, it is not. Time is not a fundamental, irreducible element or notion needed to build reality at the level of nature. It seems paradoxical to believe that time is not real, But many assumptions that humankind had made about how the world functions now need to be completely rethought. We are now questioning everything, including time. There have been so many things in physics that we thought were fundamental that turned out to be mere illusions. Depending on the time, several realities exist. Thanks for watching another episode. While you're still here, make sure to click the video on your screen for more incredible videos.